for the next couple of hours will be to play a little with logic and Datalog. So what we're going to do now is give a general tutorial, very partial tutorial, but tutorial for logic, for propositional and first order logic. I want us to discuss a few properties, just get some intuition, get us thinking a bit in logical terms. Things like negating quantifiers, what we discussed in the past. And then in the end, we're going to do similar exercises in Datalog. So we already saw some examples. That's what we did yesterday. We implemented for all emulations, like can reach all returns and all predecessors reachable from entry. And in the end, I want to do an exercise where we will do more complex for all emulations that cannot be handled with the usual negation of exists quantifiers that we used in the past. So it's going to get practical. The very first part will be theory, kind of theory, since all we're trying to do is build intuitive understanding and pattern-based reasoning. And then in the end, it's going to get down to Datalog again. So I'm going to try to connect very little Datalog and logic and get you to think in terms of Datalog through logic. OK, so you remember what we said about Datalog. We have standard evaluation. This is a slide we've seen in the past. Bodies of rules. This is really a logical expression. Comma means end. It's conjunction in logic. We will see exactly the translation of Datalog to logic very shortly. And the meaning of the rule is that every time I have proven that both this predicate and that predicate is true, then I can infer that this is true. So this is really a logical implication, this little arrow. And that's exactly how we're going to see it pretty soon. We're going to see this as a logical implication, and we're going to see in which cases the implication goes both ways, etc. And intuitively, you have an understanding of how Datalog works. And we will come back to the point of negation being stratified at the very end, because that's going to bite us. That's where we will need some logic transformations to get more powerful Datalog rules. But after all that, let's start talking a bit about logic. Who has seen logic in the past? Like at least propositional logic. OK, so not quite everyone, but almost everyone. So propositional logic is a blueprint. It's a general pattern for creating effectively programming languages. So there are many different languages that you can build using the same framework, depending on how you parameterize this framework. But you can think of logic as a programming language framework, which has standard concepts such as propositions, like P, Q, R. And what can these propositions be? Well, we can give them intuitive names. So PQR, P could be parent, or P could be adult. Like, for instance, you can say adult. And then we have logical connectives, such as implies and or not. You can say adult implies not child. And I have used here two propositions. Just like PQR there, my two propositions are child and adult. So the sentences that I can form from propositions and logical connectives are sentences in propositional logic. So these are just propositions. We give them the meaning that we want, and then we describe constraints over them using operators like implies and or not. And of course, the last one is the equivalence or equivalence operator, which is implies in both directions. And then we can have constants. Then we need to have constants true and false, or build them out of propositions. And based on those, we can have a natural deduction kind of framework, meaning that the meaning I'm going to give to all of those is the intuitive meaning. It's what you expect. Implies means implies. And means and, etc., etc. So I'm not going to give you axioms very much. or I'm going to give you a very partial list of axioms and properties, because partly I'm going to rely on your intuition for many of those. At the same time, the meaning of all these operators is not the same as the meaning in regular English. So we need to be very careful when using them. So we'll use them in a strict mathematical sense. So let's get started and try to see how we can think in those terms. And I'm sure that many of you have seen the logic and operators before, so it's going to be much more natural for you. First question I want to answer is, what's the truth table of implication? And what do I mean by truth table? Well, if you did logical design or anything like that, implication is a binary operator. So it takes two operands, A implies B, or let's write those as propositions in capital letters. P implies Q. I'll write it like this. P implies Q. And by truth table, I mean to say, if P is false and Q is false, what's P implies Q? If P is true and Q is false, what's P implies Q? For all possible cases, I want to know what P implies Q is. That's the truth table, and I want us to get the truth table for implication. So truth table for implication. P is false, Q is false. What's P implies Q?
False.
Okay, who thinks it's false? You're alone, which is a good thing because it is true. So a false premise means the implication is always true. That's one thing, that's one case where implies in mathematical logic is a little counterintuitive compared to implies in everyday speech. So that's one important thing to remember. A false premise means the implication is true. So the implication means if P holds, then Q has to hold. What happens if P does not hold? Well, nothing. So it's always satisfied. So this is typically talked about in mathematics by saying, if false anything, or the ancient Greek way, Philip of Macedonia tells the Spartans, if I come down to Sparta, I will burn all your land and murder all of you. And the Spartans just reply, if. So if false, anything. It's a true statement, but it's if false. So false is true. So similarly, of course, false and true is also true, just because false premise, true antecedent. So true consequence, true consequence. So how about true and false? If P is true and Q is false, is the implication satisfied?
No.
No. So everybody agrees that's false. And what about if both are true? Everybody agrees that's true. So in other words, we have 3 true cases and only one false case. And really, another way to remember this, or another way to express it, and this is something that's going to be very useful in any kind of reasoning you do, is that implication is just this. P implies Q is fully equivalent to either it's not P, either P doesn't hold, or Q holds. So every time you see implication, it's nothing more than an or, together with a negation of the first part. So that's something we have to always remember when we're trying to give a mathematical meaning to implication. P implies Q is the same as not P or Q. Now, here I actually say this this equivalence sign here is, I just use it here extra logically. It's not a symbol. It's not the equivalence symbol in my logic. I just use this to mean every interpretation I give to this sentence has to be equivalent with the interpretation I give to this sentence. But really, propositional logic, the standard axiom sets that we have are sound and complete. So this really here could very well be the equivalence inside the logic. So I could just as well have written this here. And that would be a true sentence in the logic itself for any interpretation. So I could also write P implies Q equivales not P or Q. And that would also work in any reasonable interpretation of the logic.
Do you have an example where you can use that? You can't use that?
Where
of logic, like, I don't know, second order or something, where you cannot do the replacement of equivalent with...
No. This is, I can always do that. I mean, if I give the standard axioms for propositional logic, I can always do that. I could always use I could always use the symbol inside the logic and prove that this is true. But I'm saying that even if it's not provable inside the logic, that's the meaning I want to give to implication. Even if I'm missing an axiom in the logic, the meaning that I want to give to implication is this. So if false anything is the thing we need to remember, or every time we see implies, also in Datalog, we should think of it as not P or Q. And I wrote it there because we're going to use it with Datalog rules as well in a little while. So what's the truth table of equivalence, of equivales? False and false?
True.
True. Okay. True and false?
False.
False and true? False. True and true? True. So it's just equality for those. It's logical equality. Okay? So there's this famous anecdote that Dijkstra used to say. He went and did a seminar to some hardware people at a hardware company, and they had never seen logic. And he writes this and says, I'm going to give you a strange symbol here. Let's say, tell me what is this operator that has this truth table? And they think really, really, really hard, thinking really hard, and finally someone raises their hand and say, I got it. It's the exclusive NOR. Which it is, but it's something much more natural, really. I mean, we should be thinking of equivalence as a logical operator. And it's a very natural logical operator, although with interesting properties. So all of those connectives can be derived from one another pretty much. So if I just have not and or, I can derive and, I can derive implication, as we saw. I can derive everything from just implication. So if I just have implication, and I have one constant, like either implication and not, or just implication and, let's say, true, or implication and false. How can I derive or and end? How can I express or in terms of implication? I want to write A or B. In terms of implication, my language will only have implication and false. Let's first try to derive negation. Let's find a way to write negation. How do I write negation with implication and false? I have a P. I want to write not P.
P implies
P implies false. Because that's, we said this is equivalent to not P or false. False can never be true, so it's really not P. It's got to be not P. So I found a way to write negation with implication and false.
So it's A implies false implies B.
So here for, let's do P or Q. What was your suggestion?
P implies false and that implies Q.
P implies false, that implies Q. Let's see. P implies false means not P or P or Q. Yes, it's correct. So I just wrote P or Q in terms of implication.
With
and
the
false.
action that not something is the something itself.
I'm talking about actual interpretations that have the meaning that we want. So yeah, that's why I write this, to appeal to our intuitive notion of what's the interpretation of all these symbols. So or is just something that I can derive from implies. How do I derive and from implies? Or from or, anyway. It's actually on the next slide, but you've seen that. The Morgan's law. So if I want to say P and Q, that's equivalent to not
P or Q.
not P or not Q. Right? Yeah. So or and are connected. I know how to write negation. I know how to write or. I can write and. I can write anything I want. And of course, the equivalence is just an implies and another implies. So that's the standard. Those are the standard. That's the standard formulation of propositional logic. And propositional logic is very, very simple because it really talks about properties that we understand intuitively as implication or as or, and, etc. So it doesn't have really very deep semantics. So we'll connect to that a little later. So let's see very quickly some properties that we should be very familiar with intuitively. And one of them, of course, is the Morgan law that we discussed earlier. But let's see here if we all know by heart the standard properties for and or. Okay, so I think I don't need to do this. So what's P and Q or R? What's the algebraic property that connects and or in this pattern? Yeah?
P and Q or P and R? Distributivity.
Okay. And distributes over or. Just like multiplication distributes over addition in arithmetic. How about P or Q and R? Disjunction or also distributes over and. That's kind of the weird thing. So P or Q and P or R. So these are things that we should just apply implicitly. We should know by heart that conjunction distributes over disjunction, and distributes over and or distributes over and. In logic, in propositional logic. And again, I'm using equivalence here or equality, but really any interpretation supports this. Since we have a complete logic based on the axioms, which I haven't discussed, really that is also something provable with regular equivalence inside the logic. This will be something that you can prove inside the logic. But let's not worry about that, because what we want to know here is what is true in our intuitive understanding.
So that's why logicians call them plus and minus instead of and ignore.
I don't know about that.
Plus and multiplication.
But plus, it's not addition and multiplication, because addition does not distribute over multiplication. Multiplication distributes over addition, but not the other way. Here, both distribute over one another. And distributes over or distributes over and.
Yeah.
Okay, so we have De Morgan's laws. So what are these? I'll write here.
I think we call them that because of the truth table.
Yeah?
Not P or not Q.
Okay, so I'm negating this, meaning the negation applies to both, but the end becomes an or, and vice versa. This is not P and not Q. Right? Standard law, again, something to remember. We will use that intuitively in Datalog programs. We will use all these properties when we think about what we want to express. And it's not just in programs. This happens implicitly in our thinking. When I want to express, I have a notion, I have a concept reachable, and I want to discuss not reachable by any. These are exactly the kinds of laws I will apply in my head. Not reachable, it will have, if it's reachable by some, and I negate that, what do I get? Well, these are the kinds of laws that I will apply. And we will see them even more in first-order logic in a few minutes. OK, well, let me surprise you a bit and show you something that you have never seen before, most likely. The rule that I wrote at the bottom. Equivalence also has lots of cool properties, but it's very often neglected when we talk of propositional logic. So here I wrote P and Q, equivalent P, equivalent Q, equivalent P or Q. So how do I read this? Well, I'll give you an axiom. Just believe me on this. Don't try to reason it out right now. Equivalence is associative. So you can read this way. Or you can read this some other way, like this. Also, I say that it has lower binding power than and and or, so always think of this as being in parentheses. It binds more closely than equivalence. And this also binds more closely than equivalence. Or you can read this as P and Q is equivalent to P, means that, and vice versa, Q and all of those are true, no matter how you read it. And let's pick the easiest one for us. What's the easiest one for us? Probably the bottom one. If the answer of P and Q is exactly the same as P, meaning I take the strongest of these two, and the strongest of these two is P.
Well, it's not the strongest.
It's the strongest. The strongest thing is something that implies the rest.
Well, you have an end, so they're equivalent. it's not like P
No,
is
no,
the
no.
strongest. If P and Q.
P and Q is, well, it could be, it works perfectly fine if P is false and Q is true.
So if you have
P and Q is false.
But no, the strongest thing in the end is false, not true.
The strongest is false, I agree.
So again, you pick the.
I'm saying if, here's the intuitive way to read this. If P is the strongest of these two, if you take two things and you conjoin them, you do the conjunction, what you get is the strongest. So if P is the strongest of these two, the stronger of these two, then Q is the weaker one, which is intuitive in some sense. But the rule can be read in any of a number of ways, and it's a true rule. That's what Dijkstra used to call the golden rule of propositional logic, that connects equivalence in multiple ways with and or. Well, let's try to see if there's an intuition with the other ones. Well, actually,
So what's the first? I think you did something on this with the parentheses.
Yeah, the parent.
yeah, the first one is really the same as the last one, right? The way I wrote it. What was I trying to do there? So, Q.
No, you wanted the P implies Q in one parenthesis, and then these parentheses with the or. You wanted the symmetric of the second one.
Yeah, I was trying to do the symmetric of the second one. So I was trying to do this. No.
Put those two in parentheses.
This.
No.
P equivalent.
P and Q in a parenthesis. P implies Q in a parenthesis.
But that's the middle one.
No, you put the other parenthesis the other way.
Okay. Where do I put parentheses?
P implies Q.
There's no implies here.
Equivalent, sorry.
Okay. Here.
Yeah.
Okay.
And the other in P,
Oh,
and
that's it.
the right part.
And the right part is what?
P or Q.
Yeah, okay.
No, you put the parenthesis there.
I don't need the parentheses here because this has higher binding power than that. So where do I put?
No, you don't put the parenthesis in the first one.
Okay.
There.
I think
That's-
that's the one you want.
Well, sure. That is definitely a different one, I think. So let's see what this says. So if the truth value of P or Q is the same as the truth value of P is equivalent to Q, then the truth,
Well, if they are equivalent.
if
then-
they're equivalent, then both P and Q are true. That's exactly identical to both P and Q being true. Otherwise, if P and Q are not true, if one of them is not true, so this and is false, then these two are also not equivalent. That's what the rule says if we parenthesize it like that.
And the same for the second one.
And similar for the second one for or though. If these two are equivalent, then one of these, if these two are not equivalent, then one of these two has to be false. No, then both of these have to be false. I'm sorry. Okay, so the point is, this is a good exercise. This is a good thing to try to work your mind around. It's excellent for just practice with patterns of propositional logic, but it's definitely not going to be something to work out with just intuition.
So these three are different, or they're the same?
All of them are true.
At the same time, or depending on?
It's an think of it as an axiom.
Ah.
This is true.
But can
Period.
we write it like this without parentheses?
Well, there's another axiom that says that this operator, equivalence, is associative, which means all of these three will have the same truth value. So I wrote it in three different ways, but it's going to be the same for all three.
So
And I also tell you that it happens to be that the truth value of this is always true. This is always true. But anything you write anything I were to write, just some big expression, equivalent, some other big expression, equivalent, some other big expression, no matter how I parenthesize it, whether I parenthesize it like that, or I parenthesize it like that, it's going to be exactly the same truth value. That's what it means for equivalence to be associative. Doesn't matter how I draw the parentheses. So usually with equivalence, we don't write parentheses. We just write this because it doesn't matter whether I interpret it with a parenthesis here or with a parenthesis here. That's what it means for an operator to be associative. Just like in arithmetic, you write A times B times C, and sometimes you even drop the dots if you have single letter variables in math, because it doesn't matter whether you do the multiplication first like that or you do it like that. So you don't even write that. Multiplication is an associative operator. Equivalence in logic is an associative operator. When I write P equivalent Q equivalent R, and not just for P, Q, R being propositions, but also for those being complex things, it doesn't matter where I put the parentheses, it's always going to be the same. Either it's going to be true or false, but it's always going to be the same no matter where I put the parentheses. But this particular one, it's always true. It's a rule. So no matter where I put the parentheses, it's true. Yeah?
Can you go over the insight on the third one with the strongest...
Yeah. So this here says P and Q is exactly equivalent to P. What does that mean? When I take P and Q intuitively, what I take is the more restrictive of the two, the stronger of the two, the stronger of P and Q. So the stronger of these two, if that turns up to be P, then that means the weaker of the two, that's the meaning of or, will end up being Q. Let's try it with specific values. If they're all the same, it's going to be easy. So if all of them are false, that's easy, right? Because P or Q and Q will give you the same thing. Will give you false all the time. So P and Q are false. Fine. So let's try something like this. We have F and true, false and true.
That doesn't work, right?
Why not?
Because it's false equals false. What equals true?
So, I'm sorry.
No, it's good. True.
So this is equivalent to true. Is that true? The whole thing. Is it true? No. So that's false. And what's that side? That's false is equivalent to true or false, and that's also false. So this works. True and false is equivalent to true? No. That's equivalent to true or false equivalent to false? No. So no is equivalent to no. Fine. If I invert it and it's really false and true, it's going to work. But this will be true. OK. The whole point of this is not something for you to remember. I don't remember it. But this is something for you to surprise you a bit and to make you get a little more familiar with logical rules. But these are definitely rules to remember. And again, the number one rule to remember is implication. There's nothing fancy about it. Implication is just that. And also what I wrote earlier. If false, then anything. If the premise of implication is false, then the whole implication is true.
Does the order in this property change? No.
The order here?
Yes.
No.
It doesn't matter.
No, as long as you always interpret this as being as binding more closely
Yes,
than
of course.
equivalence.
So we would say like P equivalent Q equivalent P or Q.
Right. Okay, so you're asking, so you're saying equivalence is associative. Is it also commutative? Yes. You can always swap it around. Yeah, but that kind of goes without saying because it's equivalence. Intuitively, we know that it's commutative. Whenever I say something equivalent something else, this is A and this is B, we also know that a different way to put it is B equivalent A. So yeah, equivalence is associative and commutative. Okay? Okay, so we got a bit surprised, but hopefully not much. So the next step, propositional logic, is simple, it's powerful, but not entirely as powerful as I would want it by any means. In fact, things that are true in propositional logic, they have kind of a derogatory name. What do we call sentences that are true in propositional logic? Mathematics, we call them tautologies. So it's like, it's a tautology. It just follows from and or. It's nothing deep. It's not a real theorem. It's just a tautology. Whereas when we want to get into more interesting logic, we have to add power. And the first really interesting framework is first-order logic, another framework for languages, for programming languages pretty much. And actually, you can form actual programming languages from first-order logic. You can say, take first-order logic as a syntax and apply it on database tables. And you get pretty much something equivalent to SQL as an expressive power. So the next framework over will be first-order logic, and it's richer than propositional logic. We have here in our vocabulary variables, x, y, etc. We have predicates, so not just propositions, not just P and Q with no arguments, but predicates just like we know them from Datalog with variables as arguments. Functions, and functions are like predicates, but really they compute new values for variables. Logical connectives and constants. And then the important thing is quantifiers for all and exist. And these bind the variables. So the variables can be something bound in a for all or something bound in an exist. And standard example, very much like the kind of stuff we see in Datalog, something like for all x, y, and z, if there's a path from x to y and a path from y to z, then there's a path from x to z. So we use, again, implication. We use all the logical connectives and or, and then we use quantifiers to parameterize our predicates. So who has seen first-order logic before? Expect most people. Yeah. Okay. So this is the standard framework. And now we'll need to talk a bit about properties. So really, the standard axioms for first-order logic are just that whenever I have for all x and then some predicate here, f of x, that implies f for any particular r. And actually, I take that back. This f is not just a predicate. It can be any complex formula. So I have any complex formula here using the vocabulary. And by using just this axiom and that one together with the propositional axioms, I get first-order logic. I get everything that first-order logic can do. So if I have any formula f here, however complex, I always know that if I replace the x with one specific r, this thing will hold. That formula of first-order logic will imply that formula of first-order logic for whatever f, however complex structure it has. And the same down here. If I have a complex formula for a specific r, this implies there exists an x f of x. And that's really the intuitive meaning of for all and exists. Right? Okay, so here are algebraic properties. Associativity. Exists associates with exists. For all associates with for all. What do I mean by that?
Such that there exists a y.
I'm sorry?
There exists an x. There exists such that there exists a y.
There exists an x such that there exists a y such that for all x, for all z, for all w, some big thing that uses x, y, w, z in it. Really, if I have this big formula that uses all of those, then I could just as well swap the order. There's no meaning. It associates and it commutes. The exists commute. So really, I could write this that way. And it will be equally true or false. The top will be equivalent to the bottom one. So I can always swap the order of for alls, of neighboring for alls and neighboring exists. But I cannot propagate the for alls outside the exists or vice versa and get equivalent formulas. So really, that's why when we write those things, we typically just group all of them together. We write for all wz exists, there exists yx such that for all wz, blah. Because the order of those doesn't matter.
So it would be different in your first one if you have there exists an x such that for all z, for all w exists y.
Say again. There exists an x such that
You have the two for all,
yeah.
and you have the other exist in the end.
Okay.
That's different.
Different than the first one? Okay. Who can give me an example of why it would be different? Or an argument why it wouldn't be? Well, first of all, let's simplify this, right? Why do we need the exists x? Let's try to come up with an example without the exists x. It's going to be the same thing. Let's say x is a constant.
It's not the second for all, I guess. Do you need?
Well, we can, yeah, let's come up with an even simpler counterexample. So does everyone see why these two are different? And let's try to come up with an intuitive sentence to show the difference. Yeah?
So the first one is there exists specific y, so that for all z something holds.
Yeah?
Well, the second one, for each z, there exists some specific y relating to a specific z, so that something holds.
So give me an example.
So,
Okay.
So
Let me give you an example, unless someone has one.
in the
For
second
each-
case, there could be different y's. Whereas in the first case, there must be a y for every z. So if you take a domain with y1, y2, y3, and z1 to 3, the first one says that it stands parent, what's x?
I'm sorry, yeah,
The part is weird.
let's do x, y.
So Okay, the parent means
There
parent.
exists a
Parent,
child where
child,
it has
or,
every parent in the world.
Increase the font.
Let's do it like that.
It's not
Well.
readable.
Okay.
No, just say
I'll just say parent y is a parent of x is the meaning of this. What does the top one say? There exists someone who's the parent of everyone.
That's weird.
Mother Earth. Nobody else. This one says everyone has some parent. Well, okay.
Could be true.
I think that's definitely true. The top one, I don't know. Depends on your philosophy. Okay? So this says there exists a single, there's exists a single value that's the parent of every x. This one says for every x, I can find a value that's their parent. But it's different y's, like people said before. So definitely we cannot exchange those and get equivalent sentences, equivalent formulas. So that's something to keep in mind when we work with for all and exists. And we will see the examples in Datalog-like things pretty soon. Here's the property that I definitely want you to remember. For all is just a big end, which means it distributes over end. And exists a big OR, which means it distributes over OR. What do I mean? And of course, not vice versa. If I have for all x, p of x and q of x, that's equivalent to for all x, p of x, and for all x, q of x. And it's really not just for predicates. These could be complex formulas. These could be any expressions. Modulo some things about free variables, blah, blah, blah. But in practice, it works. I wrote it here with single predicate, but these could be more complex things that have ORs, etc. And the same with exists and OR. Exists x such that p of x or q of x is equivalent to exists x, and let's put parentheses here so it's clear. Exists x such that p of x, or exists x such that q of x. So exists is just an OR over an unbounded number of things, and for all is just an AND over an unbounded number of things. So it distributes just the same way as a bounded OR associates with other ORs for exists. Does it make sense? The second one is not as intuitive as one may think. So learn how to apply it intuitively without thinking too much about it, because for complex expressions, this will throw you off a bit. It's not an implication, by the way. Neither is stronger. From this, you can go to the top, and from this, you can go to the bottom. It's equivalence.
Why is not the second one intuitive?
If it is intuitive, then fine. I don't think it's that terribly intuitive, because this here makes it look like there exists an x, and it's got to be an x that satisfies two things.
Either.
And here there are two different x's.
Well, you're reading it wrong then. It has to satisfy either one.
Well, that's the point. That here, let me write it that way. This is a programming language, like I said. The quantifiers create a scope. So I could very well write the second one like this. There exists an x such as p of x, or there exists a y such as a q of y. So that's what makes it a little counterintuitive, because here you're thinking, oh, there exists an x or that, but they're referring to the same x. Whereas down here, you have two different things. Q of y refers to a different variable, but it means the same thing because there exists, all you need is 1, and it's either that or that, which means you can break it in 2 cases and it's still equivalent. So this one is not entirely intuitive, I think, but I'm glad if you think it is, because all I want you is to remember this. Okay? Okay, so clearly, I think I have questions about, no, I don't. I do, but in a more complex way. So before I go to the complex one, let's do the top one with OR. For all x, p of x or q of x, and then down here, for all x, p of x, or for all x, or y, if you want to call it something different, same thing, q of x. How are these two related? They're not equivalent, are they?
No.
Now, is one of them stronger than the other? Does one of them imply the other?
The first one is stronger.
Let's, I mean, think of it for a second and tell me.
The second one is stronger.
Okay, let's see a show of hands. Who has reached the decision? Who has an opinion? 3, 4 people. Let's give it another minute, another
These two.
few seconds. Yeah. So they're not equivalent. That is not true. But is it the case that this is true, or is it the case that this is true, or none? Typically in the questions I'm going to ask here and on the next slide, one of them is stronger than the other.
I think it's none.
Then they would be equivalent, right?
No. They're not.
The bottom one
cannot compare
implies
them.
the upper one.
So let's take the bottom one in 2 cases. Let's try to build an intuition. Instead of trying to give it as an axiom, let's take the intuition. I have 2 cases for the bottom one. Either for all x p of x.
Or either.
In that case, is that true?
Yeah.
Yes.
Yeah. Or this.
Yeah.
In that case, is that true?
Yes.
Yeah.
So if the bottom one is true, then the top one is true as well. If the bottom one is false, implication is trivially satisfied. So
okay, when I'm saying that they're not comparable, I mean the sets. The down one implies that either all your objects have the p property or the q property.
correct.
Whereas the first one implies that some of them might have p property and the others will have the q property.
Correct.
So it's not like the 2 sets can be compared.
Well, whenever the bottom one holds, the top one will hold. Whenever the bottom one is true,
Yeah,
the top one is
I wasn't speaking like completely in
logic.
strictly, yeah.
Yeah. So, but in logical terms, and what throws us off is the implication to some extent. In logical terms, the bottom one implies the top one. Because if the bottom one is false, we don't care about the top one. So in mathematical logic, if I can use an OR inside the for all, but I can never say I can break it up. But of course, the other way, yeah, I can strengthen it. I can weaken it that way. Yeah.
This is an OR, not an exclusive OR. You can have the first one can be true if everything is both P and Q.
Yeah, I don't
So the second one can also. It's not like
I-
things have either the first or the second. They have.
Yeah, I was
they can
gonna
have both. Some of them they can be both P and Q. Some of them they can be P's or Q's.
As long as we're all happy. I want to know at this point if we're all convinced that what I wrote is true. Are we all convinced? Yeah. Okay. So in terms of mathematical logic, this implies the top one. Okay. But what we should remember is this part, that for all and it's equivalent if we break it up. For exists and OR, it's equivalent if we break the exists into multiple exists, but definitely not exists and or for all and or. Okay, so De Morgan's laws again, but for first order logic. That's what we used yesterday morning with our programming example when we did the for all emulations. We wanted to do for all x, and really what we used is that for all x and the property here, and I took it as a negated property, is equivalent to not exist in x, not exist p of x. Or I could write it like this. No negation here. Negation here. Because this part is negation, negation. Negative, negative, negated, negated p is p. Okay? Make sense?
Well, the first one is that you have a counterexample. The first one describes the existence of a counterexample. If it doesn't
Right.
for everyone, there's exists someone.
If
that
there
makes-
exists a counterexample, then it's not the case that for all of them the property holds.
And I think it's the same for the bottom.
But it's nicer to think of it algebraically, that you have a not outside the for all, you turn into an exists, but then you have to push the not in, and vice versa. If you want to think in terms of a for all, you can always take the exists property, negate the inside of the formula, and then put a not outside of it. So these should kind of become second nature to us. So how about implication? Implication is interesting unless you think of it this way when it becomes simpler, and then you think of all the algebraic properties. So let me write those here. For all x, p of x implies q of x. What can I say about that? How does this relate to for all x, p of x implies for all x, q of x? Let's first think of it intuitively. This property says for all the x, if p of x, then q of x. This one says if for all x p of x, then for all x q of x. Is there any relation between these two? Are they equivalent? Is one of them stronger? Yeah.
The second implies the first.
So the second implies the first.
At least.
Do we all agree? Okay, well, it's a little hard to think about it, right? So let's try to
The second
break
is
it
like
up.
the Cartesian product, right? The second.
I don't understand the analogy. The second one says, if for all of x, p of x, then for all of x, q of x. Let's say there's one element, there's a million possible x's, and one of them does not have p of x. Then this means that's false, and the second one is trivially satisfied. So the second one can be true even if just one p of x is false. How about the first one in this case? We don't know anything about the first one. The first one can be violated at any point. Just because the second one is true doesn't mean the first one is true. Let's break it up and see how nicely this can work. What did we say implication is? Implication is for all x, not p of x or q of x. So it's an or. Now that we know it's an or, if I break it into that, what do I get? What's the relation? No. What's the relation between that and that?
It's correct, equivalence.
It's equivalence? And an or? I mean, for all and or, they're not. For all and or don't play well. For all is a big and.
It's the end and the or. Okay.
There does
The
not
second
exist
one.
an x, that's p of x.
Does one imply the other? This and that?
The second one.
I'm sorry?
The second one implies.
The second one implies the first one. Is the claim? It's what we said before, right? It's exactly what we had before. For all and an or. The second one implies the first one. I know I have two cases. Either this is true, for all x not p of x, in which case the top one is true, this one. Or for all x q of x, in which case the top one is true. So I have an implication like that. So let's try to work it even further and see what we can do. So how about this one? If I write it differently, can I take the and outside? How could I write this? There exists an x such that not p of x. Yeah?
Not exist x.
I'm sorry, for all x, not p of x. Not exists an x such that
P of x.
p of x and those are equivalent. Okay, so now this becomes an implication again. We didn't have an implication before, but now I have an implication. So I can write exists an x p of x implies for all x q of x and I know that that property implies the top one.
Or is it the
But
other
that's
way
the
around?
second line.
I'm sorry?
Or is it the other way around?
Why not? Why is that?
Sorry, just
So I just said this implies that one, equivalent implies equivalent, so that bottom one implies the top one. But I didn't say anything about that part.
The last two aren't they equivalent?
Yeah, there.
Yeah, those two are equivalent. But what did I need to say there? For all x p of x, implies for all x q of x. Yeah, I don't think this one works either way. I don't think this is an implication either way. But I'll have to think about it, because I thought it was. Now, if it is, it's a different way. Well, I'll work it out offline with pen and paper. But certainly, these are not equivalent. I cannot do for all and implication like this. Well, these will turn out to be equivalent, just to give you a preview. So this is the interesting property that we want. If I want exists x, p of x implies qx, I want to prove that that's equivalent to that.
It's the inverse from what we have there.
It's the inverse from what we have here. What I showed here is the same with for all and exists. So implication is tricky because it's a negation in here, and when we take it outside, when we take the negation outside, so we take the implication outside, the quantifier changes.
So are those two, I don't know, operators, qualifiers? What's the correct term?
For these
Yeah.
quantifiers?
Quantifiers. So are those two, do they have a duality?
Yes, absolutely. Exists and for all, just like and or, they're completely dual. Whenever I have a property like this, I have the converse property. But here's this. This says, if there exists an x such that p of x implies q of x, then the property for all x p of x implies exists an x q of x, and those two are absolutely equivalent. I can go from this direction to that as well as I could go from this direction to that. Well, actually, is that true? No, that's not dual, because this is an implication. Let's work this out. Let's work this one out from the beginning to make sure. Because here I'm confused. Because this is an implication. That one is an equivalence because of exists and or. So exists and x, p of x implies q of x. That's equivalent to exists and x, not p of x or q of x. Right? That now I can distribute. So that one holds. The previous one was just an implication. The previous one was weakening. That's equivalent. So here I do not for all x, p of x, and that or exists an x, q of x. Yes? Again, equivalence. So here I introduce the implication again, and I have for all x, p of x implies exists an x, q of x, and I didn't need to weaken anything in the middle. So here I got the property that I wanted. These two are equivalent.
But we will have to prove the other way to
No. Everything I did was equivalence. I just changed the implication into or.
Yes, correct.
I used the Morgan's law here to change the exist into a for all. And I reintroduced implication because the or is now outside, the not is now outside. I mean, it's not for all. That means it's this. Not for all x px or. So I rewrote it as an implication and I'm done. Okay?
So where do we stand on the first bullet?
Where do we what?
First one, yeah.
First one?
Yes.
When I wrote it, I thought there's an implication in one of the two directions, but now I don't see it and I need to work it out slowly, so I don't know.
Just one of the two directions?
It's not equivalent for sure. I thought that it's an implication, but I'll need to work it out.
the left one implies the right one.
You think?
Yeah,
How so?
because if on the second one,
I think you're
The left
right.
one is
Actually,
true.
yeah, intuitively,
yeah,
I think this is true. If for all x, a p of x will imply q of x,
yeah, if the
then
for all x,
for
px,
all x p of x
then we can have
will
one
imply
q.
for all x q of x. So yeah, this is right. Intuitively, this is right. And we can probably prove it algebraically with a little patience to trigger the right rules. Does everyone see why this is right?
No, not necessarily.
Okay.
I try
So,
to
let's
think I try to think about it with mapping P to a person being fat and Q, a person eating well. So the first one says that if someone is fat, then he must eat well. And the second one says if everybody is fat, then everybody must be eating well. Which intuitively makes sense.
Okay. Well, here's a different way I would put it. In order to prove the way we wrote it now, I'll give you something different, which is that implication here, if I write for all x, I write this complex formula something implies parentheses something else implies something else, A implies B implies C, that's equivalent to saying A and B together implies C. Those two are equivalent. Take it. I mean, intuitively it makes sense, right? We can work it out also. But intuitively, does this make sense?
Is it the
If A implies that B implies C, that's like saying that A and B imply C. Okay? So this here says, if for all x, at any given point, at any given x, P implies Q, and I know that P is true for every point, then I know that Q is true for every point. So that's how I went about establishing intuition. We can work it out algebraically, probably by doing just replacing the implication, doing some De Morgan's law, and using the following. For all x, px, that implies exists x, px. So I'm pretty sure if we spend like 2 minutes that we'll be able to prove this algebraically with just the Morgan implication and the standard axioms, which are really what we wrote in the previous slide. But I'd rather at this point have you build an intuition, because you will not remember these algebraic rules very much, but you will remember the intuition a lot more. Okay? Are we all in agreement with this? How about the bottom one? Is that the case? Is it the other way, or? If the fact that there exists an x with px means that there exists an x with qx, then there must be an x such that p of x implies qx. Is that true? Are they equivalent? What are they? What are these two?
Well, in the second case, you have different x's. You have some x that has p of x, and then you have another that has q of x.
Yeah, this.
I think that the first implies the second. For sure. I don't know
they're
if the
not
other way.
equivalent for sure.
The first one implies.
They're not equivalent.
So is the first.
We can use the bottom one to help us a bit.
So, in this one, say some x has
So if there
property
exists a
p,
fat guy,
and some no. To take this example, some x has this property, and some other x has some other property. We don't know for sure that x has both properties, but having both properties is not the arrow, is the end. So don't think that because there are two different x's, and they don't, it's not like one x with two properties. It can be two x's, one with p and the other with q. So you can say that x is both p and q, but we don't want that. We want p arrow q. Right.
I would, since we already proved that the tough one, which is the equivalence at the bottom, I would suggest we use that to think of these two. The first part is the same. What's the relation between this and that? Between that whole thing and that whole thing. Because the bottom whole thing is the same as that. We proved it. It's equivalent. We did it before. So what's the relationship between those two? Which one is weaker and which one is stronger?
The bottom one is stronger, right?
So the bottom one is stronger?
not really.
It's under a negation because it's in the first part. So that thing normally for all is stronger than exists.
The bottom one.
But it's an assumption. For all is an assumption. It's a negated for all. This is a negated exists. That's what we get. Why do we get that? I'll do it on the other board. It's the implies that fools us. And that's why we always should break up logically the implies into not P or Q, and we should watch exactly where that not is applied. And just hold your breath, because in just one slide we will see all this in Datalog. So, okay, so
then the answer is not that the right one implies the left one.
That's the answer.
Well, you said that if you have A implies B and B implies C, then you don't have A implies C. You have A and B implies C.
No. That's not what I said. I said if I have A implies B implies C, that's the same as A and B implies C. I didn't say if I have A implies B and B implies C, then A does not imply C. A implies C. Okay, so let's establish the relationship between these two so I can convince you that that one is stronger. Why is that one stronger? The top one is exists an x, P of x, implies blah. I don't care. I don't care about the second part. So this here is equivalent to not exists x px or blah. Correct? Which is equivalent to for all x not px or blah, which is implied by for all x not px. Okay, hold on. I started from the top one. Confused here. I think I need to tick the blah in some way and use some of the property that I had before. So let's look at this again. Let's start the other way. For all x, px implies blah. Can I do it like that? So I'm trying to take the blah in. So I'm going to say there exists an x such that p of x implies my blah. Okay, I take it back. I'll need to work that out as well. So I'm also a little rusty here. So.
I mean, it's quite risky to just think them without analyzing the implications. So
It's quite risky, but the point is, I'm pretty sure there is an implication this way. I just don't remember exactly the method to go about proving it. I will need 5 minutes offline to do it. So.
Well, I think the problem there is your last step. On the board. Because actually you have parentheses around exist x and not p of x. And or blah is separate.
Yeah, but it's an or with exists. So I don't really care. I just rename all the variables here and take the blah in and I'm fine. I can take always the blah inside the exists if it's linked with an or. So there needs to be some trick to play there like that to work out the proof.
Can we just say that, starting from the right one, that the first part says that there exists one x, let's say it's x1. So it says px1 for some x1. And the second one says qx2. So it's either not px1 or qx2. In both cases, it implies the left part.
I don't know.
Because if not px1, then there exists some x, which is x1, that px will imply q of x, because the left part becomes false.
Actually, I think this may be incomparable. I'm not sure that this is an implication. I think these two may be incomparable. Let's work it. I think we can work it out offline.
Could it be that the bottom one is equivalent to their exist on the left?
Yeah, but the bottom one, we proved it already. That one for sure is equivalent. But I'm wondering if there is. I thought there was an implication like that, but now I no longer think that. I actually think it's not. There's not one. Yeah.
In the left side, yes. The last line implies that there exists an x.
Okay. So I'll do the interpretation implication. There exists an x such that not p of x.
Or blah.
Or blah. Okay. But that doesn't.
Which is what we have in the right side of the word.
Well, the blah is like that here, which means we had that here, right? Huh.
So when we are equivalent.
So yeah, I think we proved it.
So there's not.
So I think we proved it. So that says, So we started from this, equivalent, equivalent, down here. From here, it's this one. So next, not P of X or blah, yeah? And then we go all the way to equivalent to the bottom one. Yeah, so it is true, and we proved it. I can't quite see how, but we did it. Let's recap. Let's do it again. We start from that. The second part. Exists an x P of X implies that whole thing I will call blah. Exists an x P of X implies blah. That's equivalent to not exists or blah. Equivalent to for all x not px or blah. Implies exists an x such that not px or blah. And because I have an exist, no, well, exists an x not px or blah, yeah. I can take I can write that now as not for all x px or blah. And I can write that equivalently as for all x px implies blah. But I have already proven that for all px implies blah is equivalent to the first part. So I proved the implication. So that was our proof.
I'm not sure. You imply.
Tell me what's the problem.
I think you are proving that A implies A.
No. I started from here, which is this part.
It's the other part.
No. I started from this one. I started from the right-hand side. It's this big thing implies some other black box thing. Here are the parentheses. The implication here is inside the exists. The implication here is outside the exists. So I took the top, this part. I proved that it implies that one. I have already proven that that one is equivalent to that one. So I proved that arrow, or Nefeli did. But the point is, you get to see that this is very tricky. So we need to be very careful with implication because it has this hidden negation. And we need to treat it very carefully when it has to do with quantifiers because whether the negation is inside or out will make a huge difference, and the same as implication. That's also what I expected, and since we saw the proof, I'm pretty confident this is correct. But let's try to see it intuitively. What's this saying?
The first or the second?
The fact that this implies that.
The existence of some.
How can this be violated, this implication? This implication is only violated if there exists an x with P of x and there does not exist an x with Q of x. So for all x, it's not the case that we have Q of x. So the only way to violate the second part is to have for all x no Q of x, not Q of x. Otherwise, we are okay here. If we have even a single x with Q of x, we are okay here. So this is a very strict condition, the second part. It's violated only if for all x, not Q of x. So if the second part is true, so there's no violation, then isn't it the case that the first part is true? It's never the case that if we don't have not Q of x for all x, then that implication is satisfied as well. So that's why this makes sense intuitively. Anyway, we got confused enough, but we also saw how we're working these things out with the properties. Okay? Okay, so Datalog with all of that stuff. Every time we have a rule of this form in Datalog, QXZ, RZY, PXY, or any body of the rule, any more complex body, we really interpret it as an implication, right? So here's one way to think of this. Take all the variables that appear anywhere in the rule. Think of them as universally quantified for all. So for all x, y, z in this case, it is the case that QXZ and RZY implies P of xy. Okay? So for this particular one, let me also write it a different way. It's a little counterintuitive.
You have it right afterwards.
I'm sorry?
Yeah, it's you have it in the next line.
No, I don't have it in the next line. The next line is the opposite implication. Next line is the P implies the rest. So what I want you to do at home is think about why this with for all x, y, z is equivalent to that, provided that z does not appear after the implication. Provided that z is a variable that only appears in the body of the rule. And you'll use exactly the same properties as we did before. All use your intuition. Try to convince yourselves. Try to see if that's true. I'm giving it to you that it's true. The point is, this only holds. I cannot change a for all into an exists, or vice versa. This only holds because that z does not appear in the pxy part. The other part is the Datalog rule is not just an implication this way. Because Datalog does bottom-up evaluation, we are guaranteed that anything that holds will have some rule to support it. So really, if this is the only rule that derives P, I also know something of the converse. I know for all xy, there exists a z such that P of xy implies that. Again, what's the general case? The general case is I take all the variables that appear in the head of the rule. These are universally quantified. Any variables that only appear in the body of the rule, I take those as existentially quantified. And then, logically, I also have the converse implication. That if the head is true, then the body also has to be true.
That would be in this junction if you had others, right?
What would happen if I had other rules is the question. So let me remove that. So I put the extra case. Let's say I also have another rule that establishes P. Let's say I have P of x, y follows from something else. W of x, z, and s of x, y, z. What would happen down here to this one?
Or the body of the others.
Right. For something to hold about this head predicate, it has to be derived by one rule or the other.
At least.
Or w, x, z, and And of course, no, it's the same variable, so we're fine. So that's the meaning of Datalog if we think about it in terms of logic. So the obvious meaning is the first part. The non-obvious meaning is the second part. If you want to think about why the easy relations that you defined yesterday, like you had some easy relations yesterday, reachable from entry and can reach return. If you want to prove that those actually compute, there exists some entry that can reach me, you will need both sides of the implication to prove that. You cannot prove this just with this. You will need the other part as well to prove that this rule actually computes an existential. So we already saw that some things are much more intuitive if we just think of them in regular plain language terms when we express them in Datalog. But other things will be much more intuitive or much more automatic if we use the algebraic properties of logic. And you'll need to have some of these properties in mind when you're working with Datalog. You may, but definitely at the very least, the De Morgan laws for exists and for all will come very, very handy. Okay, so now let me go into an exercise that we can actually continue tomorrow, since we're running out of time here. Actually, we probably have enough time. So you already did yesterday a plain for all emulation. We did can reach all returns, or from all predecessors reachable from entry. You already wrote that. Let me do a harder exercise for you. Consider a var points to relation that's flow sensitive. That means it's defined not just for every variable and heap. It's defined per program point. So I have a relation of the form variable var points to abstract object heap at instruction I. And then I have my next relation like yesterday. Next instruction I1, I2. And I'd like to write something that looks very simple. A variable points to an abstract object at instruction I, so var points to heap at instruction I, if, and only if, it points to that same object at all predecessors of I. And predecessors are all the instructions in the next relation that have I as the second part.
So must point.
No, it's not a must point. Well, yeah, sure. Think of it as if I'm merging two control flow points, then the bottom node at the merge of two control flow points will need to take the intersection. So it becomes something like a must relation, yes. How would we write that? So here's the straightforward way you would do it. The way you did it yesterday, you would say, you want to prove, here's what you want your rule to compute. For all predecessor P, var points to, that's the predicate, VPT, P, comma, V, comma, 8. And you want to say, if that's the case, you want to prove, you want to establish VPT. Let's write it this way. For all P. Next, P comma I implies VPT P comma V comma 8. And you want to prove from that VPT I, comma, V, comma, 8. Well, not prove it, but you want some rule that in its body it's going to have a for all. And you cannot really do that. So the way you would compute that yesterday would be to say...
So can I ask something?
Yeah.
The issue that I always have with logic is, in cases such as this, how do you decide if you have for all P next P implies VPT or for all P next end VPT?
Which implies.
Okay, so here's the thing. The way you think about it intuitively, you have for all x such that condition of x, you have some precondition, and then you have formula that has x in it, right? And you have similarly with exists. And in fact, in first order logic, very often we have these formulations. We have some precondition. It's not really all the x's, it's all the x's that satisfy a condition. Fx. So for all x that satisfy this condition, f of x, that's like saying for all x condition of x implies f of x. Here, it's like saying exists an x, condition of x, and f of x. When you have a for all, what you think in your mind as a precondition, like when something selects a subset of the x's, that's like saying implies. So for a for all, you always translate your intuition of limiting the p's into an implies. So here, you want to be sure that for all predecessors meaning for all the p's that are predecessors, you have that. If we had an exist, it would be an end. Okay, so getting back to the top one. You're thinking of writing an exists P such that not this implication. And what's not this implication? The implication on it by itself is the same as not next PI or VPT PV8. So by negating that, we get next PI and VPT PV8. Did I say that right? Okay.
No.
Where did I make a mistake?
Needs and the VPT must be negated.
Okay, negated, yes. I forgot the negation here. And now you think this is easy to compute, right? We can write this in Datalog. Because really, what you're saying is, I will compute this concept, the existential. That's exactly what you did yesterday with your can reach all returns. So you will say, predecessor does not point to variable. So let's write that rule. Let's write that Datalog rule. Predecessor not VPT P, comma, I, comma, V, comma, 8. And let's not care about how big this relation is going to be, because it can be huge, but let's not worry about that. And your Datalog rule would be...
Do you need the
Why are there 4 arguments?
I'm sorry?
Why are there 4 arguments to pred VPT?
Let's keep all of them, all the useful one. Well, I don't really need the p. I don't need to remember the p. Some predecessor of I does not satisfy what I want. So next p comma I and not var points to, I'll expand that. P comma v comma 8, and let's say I compute this for all variables v and all allocation sites 8 or heap object 8. Isn't this exactly what you did yesterday? So you define this, which is the red part, and then to express your rule up here, you would write something like var points to I comma v comma 8 follows from not the negation of predecessor, not var points to I comma v comma 8. Okay, so that's what we did yesterday. Why does this not work? There are multiple reasons why this will not work, but
because you need to say that I is an instruction, V is a variable.
Okay, if I say that, let's say I say that I is an instruction, V is a variable, 8 is a heap object. And let's say that the definition I gave you here makes sense. So an instruction with no predecessors can have the variable point to anything. So let's remove these kinds of objections, which are the easy objections. Why does this approach that we saw yesterday as the right way to do the for all emulation? And we used it already in 2 relations, and it's well founded in logic. Why does this not work in Datalog? Can you think of a reason?
Why it doesn't in the engine, or why it
In
doesn't
Datalog
in
in
actuality?
In the engine or any...
So it doesn't work because it will invalidate itself.
It doesn't work because it means that the var points to relation depends on the pred not VPT relation, which depends on the negation of the var points to relation.
But that comes from the fact that you might have loops in the basic blocks. So if you didn't, the engine couldn't find that there is a stratified negation, but there is actually stratified negation if there is no loop.
Sure, but in this case we do not have stratified negation. I mean, so stratified negation means stratification in the rules anyway, regardless of what the input facts look like. I mean, we can have more complex parts, more complex notions of stratification, but that's not what we're talking about here. The stratified negation that we're talking about in Datalog is stratification in the rules. So the problem here is var points to depends on itself under a negation. And this is an actual problem in actual programs because you can have cycles in the instructions. So you can have some var points to that invalidates itself. So the approach that we saw yesterday will not work for all kinds of for all emulations. So what we can do, what I can try to explain now is how to do this really quickly. And we can look at some code about it tomorrow, because we have lots of code that's like that in various parts of Dupe. So does everyone see the problem, first of all? So the difference between this specification and this is that here we needed to negate something that came from the input. It came from an earlier stratum. Here I need to negate myself. In order to compute var points to for instruction I need to compute the negation of var points to for a previous instruction P. And I don't really know that this p will never end up being this I. So the engine will reject my program. Yeah?
Something else. I'm not sure why we translated that specification there to that formula over there. I'm not sure I get it.
So we said a variable points to an abstract object at instruction I if it points to that same object at all predecessors of I. So we said I want to compute that for all predecessors of I, the variable points to heap. That's the concept I want to compute in the body of a rule. So I want a for all in the body of a rule. The body of a rule, the problem is that the body of a rule is under an implication. If I want a for all in here, it's not the same as a for all the way out. That's the meaning of the Datalog rule. There's a for all the way out. When it goes inside, it will become an exists. So we can do, in Datalog, we can very easily do exists for the body of a rule, but I cannot do for all in the body of a rule. If I want to do for all in the body of a rule and take it out, because the body is under an implication, I'll need to negate the exists. So to take this for all, I negate it into that. I wrote it as that, using De Morgan's law. That's what we did intuitively anyway. And I expressed this concept, the red part, and then negated it. So that's the Datalog that will give me exactly the body of the rule I want. That's the body, and I infer the head. So in theory, if this were to work in Datalog, this would be exactly the expression of this. Okay? So what's the answer? The answer is, very briefly today and more tomorrow, that we can emulate for all in Datalog as long as the things we need to iterate over are finite and we already know them, as long as the number of those p's is bounded and it's not itself computed by the rules, by these rules. How do I do it? I will do it by saying, does this whole thing hold for the earliest p? And then I will say, if it holds for one p, does it hold for the next one? So here's how I will do this exact concept. This assumes that I have an ordering relation on instructions. So any two instructions, I can order them. But I would write this the following way. Okay, so this is just groundwork. I just defined the concept of the first predecessor of an instruction I. Right? So it's a predecessor, and it's not the case that it's the non-first. And what's non-first? There's some other predecessors that's less than it. This less can be any arbitrary ordering relation. So as long as I have an arbitrary ordering relation, I can emulate for all in Datalog. And because of this negation, that's why I need all of the predecessors to be finite, to be pre-computed. I cannot compute this next relation as part of my rules. So now I have the concept of first predecessor. That's just background. I'm just using this. And now I will say first predecessor var points to p comma I comma v comma 8 if first pred p comma I, and I have var points to at instruction p between v and 8. And here, my next relation will be up to predecessor var points to base case. Well, actually, I need to do more, right? I need to define next predecessor as well. So let's forget that for now. Up to predecessor is if Can you see where I'm getting at? The tough part is really done. If I have defined the concepts of first predecessor and for each one, what's the next predecessor, then I can do a for all emulation by saying the predicate holds for the very first of the predecessors, and then I can see which predecessor it holds up to, and then go all the way to the last one. So let's complete this by adding next. I'll add it on the other board.
So we are doing manual stratification.
You can think of it that way, yes. It's not really stratification. Doesn't change really, doesn't give you a stratification of the logical rules of the program, but it gives you yeah, you can think of it intuitively as manual stratification. Yes, I think so. Okay, so I'll avoid defining next predecessor for now, because I will either need to use negation in a complex way, or I'll need to use aggregation, take the minimum of the other. But imagine that I can do this. I can define the next predecessor, just as I defined the first one. Think of it as the next one is the one that's higher than the current one, but there's no other one that's between them. You can always define next predecessor with two negations. In practice, in actual code, we do it with aggregation. We just say the next predecessor is the minimum one of those that are greater than it. And if I have this relation, I can define all predecessor VPT I, V, 8 by doing this property holds up to a certain predecessor, up to pred VPT P, I, V, 8, and it's the case that no next predecessor exists for P.
So this one is the last predecessor?
Yes. So if this is the last predecessor, then I defined the concept I wanted. That concept was the red one I had before. and I can just say this. I can just use that now. I mean, equivalently, I could say what I wanted, the property that I wanted originally. Var points to I, v, 8 if up to the last predecessor this property holds. I don't need this intermediate concept, the all predecessor VPT. Did I confuse you? Yes. Okay.
In terms of graph traversal, how would it look like?
In terms of graph traversal. So let's say you have predecessors in a control flow graph, and the property we want is for all of those predecessors, the variable has to point to a certain object so that it points to that object down here. And we take an arbitrary ordering of the predecessors. Let's say that's 1, that's 2, that's 3. And what I'm doing is I first prove the property for this predecessor. That's the first predecessor. That's the base case of this. And then from 1, I try to see if the property holds for the next one, for 2. If it holds, I say up to predecessor 2, the property holds. And from 2, I will say, will the property hold for the next one? Up to predecessor 3, the property holds. And then for 3, I know it has no next predecessor.
It's something like induction.
Yes, it's like induction. And if it holds for 3, which has no next predecessor, then I go and say the property holds down here. Or more generally, the property holds for all. So that's how in Datalog we emulate a for all. So by the way, the technique I just showed you, that's for the proof that Datalog can emulate all polynomial time algorithms, you need to use that. Datalog can emulate all polynomial time algorithms only if you assume that all the elements in your universe are somehow ordered. So you can go and do for all one by one over them. So that's a pretty important technique for expressiveness. Yeah?
And yesterday, when we emulated for all, why didn't we enumerate?
Because we had no recursion through negation. Here you are defining the var points to property, the var points to relation, in terms of var points to in all predecessors. So var points to is an assumption, but it's a computed relation. Whereas yesterday we said reachable from all entry nodes, and that part was computed earlier.
So each time we have negation through recursion, we can break this, we can make it work by pre-computing and ordering.
Yes.
Well, not each time.
Not each time. The ordering itself has to be finite, has to be set before you compute these rules.
So if we can enumerate in a finite way, we can implement recursion and the negation.
Yes.
Okay.
So whenever you can, you use the technique we saw yesterday. You just use first order logic, and instead of for all, you compute an exists and you negate it. When you cannot do this, because the property you are computing is itself dependent on itself in some way, you have to use this technique. This technique is hair pulling, I understand. I just want you to understand the general idea, because there are multiple examples in the code. So if ever you need to use it, you just copy one of the examples and you do something very similar. But you need to be familiar with the idea that this technique exists, because it is essential for saying that Datalog can do anything you want. In order for Datalog to do anything you want, you need to use this concept of enumerating things one by one sometimes. Okay? That makes more sense, or?
I think an example with the other case is if you had like a var points to information is propagated only if at the previous point you didn't point to null. So you cannot enumerate all the objects that you point in the previous step. And you cannot do this trick.
Cannot do this trick?
If all the objects that you point in the previous point are not null, then you propagate the information.
Correct. Or it could be something like if all your colors, instead of control flow graph, which has a finite number of previous instructions, if we had a call graph and we had some function foo and all its colors, and we wanted to say something holds at the beginning of foo if it holds for all its colors, that we cannot say because who is a caller depends on points to information. We compute the call graph in mutual recursion with points to. So I cannot have points to at this point depend on who are the callers because who knows? Maybe the point to value that I will have here will create a new caller and that's going to violate the for all here. The points to that I have here because of some virtual call later will show me that there's one more caller of me. And suddenly the for all property doesn't hold, which means that I shouldn't have proven the points to in the first place. That's another example of when I cannot even use that trick.
So since the locations are finite and they're also ordered.
It's not just finite, they are computed in a previous step. The locations are fixed. The next here is fixed before I get to this computation.
But then you can translate this into first order logic and then prove by induction.
You can always prove that this is correct, yes. There's no issue about proofs, but proofs can be hard. Okay, so I know we got a bit confused, but this is the deepest we will get to logic and Datalog. So it doesn't get any harder than this. So you now saw the full complexity. So tomorrow is going to be easier. Because tomorrow we're going to talk about practical optimization, how to make our programs thousands of times faster by picking good indexing. And thousands is not an exaggeration. Like a bad program versus an optimized program can be tens of thousands of times faster. And then we will see in the afternoon tomorrow similar concepts, but not in Java bytecode, but in LLVM bitcode, which is our other framework, which is very good for C and C++. Any other questions?
Is that method translation, let's say, you mentioned in your slides?
No. This is nowhere in the slides.
So take a photo.
Take a photo, but there are multiple examples in the code. So have you taken a picture of this, or are you okay with this? We have a camera. So.
Are there examples in the code they have?
In the must.
Okay.
The must analysis. So under analysis, if you go to must point 2, look for all emulations at the bottom, and there are about 15 different examples of this. For all returns, this holds. For all this, for all that, for all predecessors. There are multiple patterns that use this. Okay.
So are you going to upload your slides to Slack or to
Yeah, I can do that.